For task 1, we focus on applying the first order differential equation to model population growth in Malaysia from 1980 to 2010. We use the multi-share model, which is based on the equation dP/dt equals to Kp, where P represents the population and K is a constant that describes the growth rate. This model assumes that the rate of change of population is proportional to the current population. And according to the data from the World Bank, Malaysia's population in 2010 reached about 28.7 million. This model will help us to predict and analyze the population growth trends over time.
For implementation, we obtain secondary data from the World Data Bank and observe the total population in Malaysia from the year 1980 to the year 2010. Based on Table 1, the population in Malaysia increased from year to year. To model this growth, we use differential equations and applied the multi-share model. This is Table 1 that shows the total growth population in Malaysia from year 1980 to the year 2010. Then, let P of t represent the population at time t. Since the rate of growth is proportional to the total population, we solve the differential equation using the method of separable variables and found the general solution. P equals A times E raised to the power of K times T, where A equals E raised to the power of C. Using the initial condition in the year 1980, where the population was 12,983,363, we found the value of A to be the same as this population. Next, using the data from the year 1981, where the population was 13,399,203, we calculated the constant K, which is 0.03153. Therefore, the particular solution becomes P of T equals 12,983,363 times E raised to the power of 0.03153 times T. This equation was used to estimate the population in Malaysia from the year 1980 to the year 2010. Table 2 shows the comparison between the actual population and the estimated population based on the model.
In this graph, the red line represents the actual values, while the green line represents the estimated or calculated value based on the model we use. In the beginning, the actual values and estimated values are quite close with each other. However, as time goes by, especially after around year 10, we can clearly see the gap between 2 points started to widen. This shows that the model becomes less accurate in predicting the actual population. The difference between these 2 points happens because the model assumes a constant rate. But in reality, factors like healthcare, economic changes, and policies affect the population growth differently over time. Overall, although the model gave a good approximation in the early years, it becomes less reliable in long term.
Hence, we'll further our discussion by discussing how we use the particular solution in order to predict the future and the past value. In this step, we will predict the population at 2011, which is at the value of t equal to 31. We will insert the value of t equal to 31 into our particular solution, and we will obtain the predicted value to be 20,862,822. In the next step, we will use the particular solution to obtain the past value at year 1970, which is at t equal to -10. By inserting the value into our particular solution, we will obtain the value of 11,141,409.
So, first, we can see that there's a slightly noticeable difference between the estimated and actual values, especially starting from the year 2003. To understand the accuracy of the model, we calculate the percentage error. When t equal to 13, which represent the year 1993, the estimated population is around 19,561,410, while the actual population is 19,332,664. Using the percentage error formula, we get an error of about 1.18%. Since this is below 5%, it shows that the estimated model is quite accurate. However, the difference between the calculated and actual value happens because of environmental factors like healthcare improvement, policy changes, and shift in socio-economic condition. Our particular solution assumes a constant rate, so it doesn't fully take these changing factors into account. Looking at the past, population growth was influenced by economic stability, healthcare access, cost of living, and debt rates, all of which slow down the growth rates. In the future, population growth is expected to be influenced by many factors including climate change, cost of living, government policies, technological advancement, and family planning initiative. These factors could lead to a decline in the population growth, which made it difficult to predict accurately.
To conclude, this task shows how first-order differential equation can be applied to a real-life situation like modeling population growth. The Malthusian model, which we use, assumes that population increases at a rate proportional to its size. By applying this model to Malaysia's population data from 1980 to 2010, we gain a better understanding of how mathematical concepts can help in predicting trends and making informed decisions. It is a useful tool for planning future needs such as housing, healthcare, and infrastructure. Overall, this task highlights the importance of math in understanding and managing real-world problems.
Hi, so moving on to part 2, we are asked to find the area under the graph of this equation, and we are given the x, and we are given the range of x, which is negative 9 until negative 3. And we have to use 4 subintervals and 8 subintervals, so I will show you on how to solve this with 4 subintervals. We have to first find the weight, which is h. In order to calculate the h, we have to use the formula of b minus a divided by n, which is 4, because we have 4 subintervals. For b, we have negative 3, and a, we have negative 9. So negative 3 minus negative 9 divided by 4, we will get 1.5. So first of all, we have to fill this column of n from 0 up until 4, because we have 4 subintervals. Now, to find the x, we will use a special formula, which is a plus in the bracket n multiple h. We will get negative 9. To get the rest of x, just repeat the same step until we get negative 3. And then to get the fx, we have to type in the equation that is given to us, just like up here. And then just substitute the amount of x into the formula, and we will get the fx. So to get the rest of x, we just have to click this and drag it all the way down here. And then Excel will calculate it automatically for us. So to get the coefficient, it is part of Simpson rule that we use 1 for the first x and the last x, and then 4 for the odd number, and 2 for the even number. And then we proceed to find the fx multiple the coefficient. So to get the fx multiple the coefficient, we just have to click the fx and then multiple the coefficient, and we will get the answer. So to get the rest amount of fx multiple the coefficient, we just have to click here and drag it all the way down here just as before. Now we have to find the sum of fx multiple the coefficient. So just type in equals to sum and choose the first option, and it will automatically calculate it for you. Lastly, we want to calculate the approximate area under the graph. We have to use the formula of weight divided by 3 multiple the sum of coefficient multiple fx, and then we will get the answer. So this is the graph that we got after using the Desmos website. So how to use this website? Just substitute the amount of a, b, and n, which is a, we have negative 9, b, we have negative 3, and n equals to 4 because we have 4 subintervals. As you can see here, the area under the graph that we got using this website is the same as the one we got from the Excel. Now that's all from me. Now we will show you on how to solve this equation with 8 subintervals.
For part B, the solving steps are similar to A, but the difference is the number of ordinate, which is 9. So we are using the subinterval. For this part is 8 subinterval. To find weight, it is same in A, but the difference is for A is equal to negative 9, B is equal to negative 3, and N is equal to 8. Thus, we calculated for our weight and we got 0.75. Next, to find the x, it is the same as in part A, but the difference is the weight. So we just change the weight to calculate the x. So to find the value of fx, we just substitute the value of x into the equation given. It is the same when we want to find the other fx, so we just substitute the value of x respectively. So for the coefficient, it is similar to A, just like what IZZAH said before. Next, we just multiply the coefficient with fx. Therefore, we sum the product of the coefficient and the corresponding fx values. So, to find the approximate value of the definite integral, we just divide the weight by 3 and multiply it with the total of the coefficient multiplied by fx. For the graph, we inserted the equation given into Desmos. We chose the limits of integration as negative 9 and negative 3, where negative 9 is a and negative 3 is b. For n, which represent the number of subintervals, we chose 8. After that, we obtain the approximate value of the definite integral of the function, which is Sn is equal to 60.5.70 and so on. When the number of subinterval is high, the accuracy of area is high too. To be more precise, there are only 4 parabolic top elements to be calculated when n is 4. while compared to 8 subinterval, there are 8 parabolic top elements to sum up the area of integral. Thus, the accuracy of 8 subintervals is higher than 4 subintervals. In conclusion, when the number of intervals increases, the accuracy of area approximation also increases. It will result in different value for the area depending on the value of n. And I think that's all from us. Thank you.